Hey, everybody, and welcome to this live session of High Performance Delta. We're joined today by KyJah and Raki Rahman, and we're going to kind of just kick things off, getting to know these guys. KyJah, do you want to get started?
Yeah, so my name's KyJah. When we started this project, I was, an engineer at a company called Aware, which is now part of Mimecast. And then, I ultimately came to Next Data as a contributor to Delta RS. But how this project initially started actually was a funny story. At Deus in I think it was 2023 when I was contributing to some of the Delta RS projects. Someone made a joke about implementing it in .NET, and I said that crazy thing. Oh, that'd be easy. And well, it it wasn't, but it was possible. So I did that implementation, and it was pretty useful for my use case. And it just kind of sat there for a while, because after I switched from being a .NET developer to a full-time Rust developer, didn't really have as strong of a use case to continue working on it, and there hadn't been as much organic interest. And then one day, Rocky showed up and said, "Let's do something crazy." And I was like, you know what? Tell me what's on your mind. And he's really helped, evolve it into some more interesting use cases, which he'll get into later. But that's kind of me and my experience with this project in a nutshell.
Awesome. Raki, what about you?
Yeah, thanks, KyJah. So as KyJah mentioned, Raki at Microsoft on a SQL Server team for Azure Arc. So basically, we have customers across like millions of data centers that kind of send us data and work with our product. And one of the use cases that I had was we have Event Hub, which is kind of the Microsoft's version of PaaS Kafka, where we collect all sorts of telemetry data and metadata. And I needed a way to get it into Delta because our team uses Spark, Databricks, Fabric, Synapse, like all the Microsoft kind of Azure flavors of Spark and otherwise, and we needed to get the data into Delta. And originally, I was running it. The story is actually very similar to kafka-delta-ingest, which is we'll chat about it. But I was originally using Spark in order to get the data in, and then Spark gets expensive because you're paying for a cluster just to read-write data, which is not the best use of Spark in my opinion. And I was looking into what we can do, and I found the project that KyJah mentioned that he started, which exactly fit my use case. And along the way, I discovered I got a chance to work with the Delta kernel folks who are building kind of the kernel layer in Rust, which allows you to do read-write operations from any database. Like, for example, DuckDB uses it. And, I was basically reinventing KyJah's package. And then I realized, wait a second, this thing exists. So I took all my experience with the Delta kernel and then contributed into the repo, which used to be a wrapper on Delta RS. And, we have some good use cases. My team is using it in production today for about 2 months now, and it's been running stable. We can chat all about, what kind of scale we have. I have a demo. But yeah, it's been a great community over the last, I would say 2 or 3 months, KyJah. And then, I had a chance to contribute. And we have a few things coming down the pipe with things going to help solve other people problems in C# and .NET. Yeah.
That's awesome. All right. Do you want to kick it over to slides, or do you want to start talking a little bit more about like the steps it took to basically take this to production?
Yeah, I can probably provide like a quick walkthrough of the current state of the repo and like what it wraps and how are we integrating with Rust, and KyJah if you wanted to jump in. And then just because I don't think not everybody is understanding, like how do you go from .NET to Rust without re-implementing the Delta transaction protocol? And then I can show exactly how my team specifically took that NuGet package and we're kind of using it in a more like distributed fashion. So basically we're like throughputing really high throughput parquet files. And I can walk through, what are some of the challenges that it took me, some hacks I had to do, and how we plan on, mitigating those hacks in delta.net over the next year using the Delta kernel. So I can share my screen and we can look at a diagram if that's okay, Scott.
That's perfect. Let's do it.
All right, sounds good. Just bear with me for 1 second. Present, share.
In the meantime, for people who haven't been in the C# community before, do you want to just talk about what NuGet is so they know?
basically, you know what jar files are for Scala and Java. That's basically a NuGet package for delta.
Yeah. So it's like Maven, or npm, or crates for Rust. So if you, I guess, 'cause I can lay some groundwork about where we started and where we are now. So initially, right, the initial implementation was pre-kernel. We were still waiting for kernel RS to even, become a public repo. But just to get something out there, started with, a wrapper over Delta RS, and the way that works is, for the .NET folk familiar with pinvoke, is that's basically how you load a C or native library into .NET. So because Delta kernel's FFI bindings didn't exist, I had to write a bunch of custom FFI bindings, and that's what that Delta Lake Rust Bridge project is. And it's a bunch of code that I wrote to try to simplify the use case from .NET to Delta RS, because Delta RS is very strong. It's Rust. It is the Rust experience. So I tried to keep it more of a SQL-based experience for people who are more familiar with using, Entity Framework. And that was my original implementation. But when we created the project initially, one of the initial discussion points was, once Delta kernel RS is ready, we should begin to switch our implementation to use that. So, Delta kernel is very close to being a full replacement for Delta RS. There's still features missing from the FFI area of like a proper interface for wrapping the transaction protocol, but that's coming. There are some pull requests open to get us there. So once those are in place, we can begin to really remove the Delta RS wrapper and then just focus on a kernel-based wrapper, which will allow us to do things like write the parquet in native .NET code, so we don't have to send really large packages across the C boundary, but still leave the transaction writing to the engine, or anything that's semantically Delta can still be handled by the underlying kernel code, whereas, legwork that's really not worth shuttling back and forth can be handled within the .NET code.
Just add to what KyJah said. So this is like, I'll get into some pain points that I had to look into when I was trying to like use this at like pretty massive scale. Like we were pushing the limits of a Event Hub 16 PU. From what I like see, I haven't worked with pointers much like in .NET before this project. Like, I did like C++ back in like university, but like people don't use pointers. Everyone uses garbage collection. So, when I was working on this project, one of the things that I saw was like, when you have a language and you're trying to go from like one language to another language, which is essentially Rust, and like you're trying to shovel like terabytes of data per minute, right? There's going to be bugs in the libraries that you use. Like, for example, I found a bunch of bugs in the Apache Arrow actual like library, like the one that wraps .NET. And I was facing like memory leak issues and issues with the memory allocation and stuff. On different operating systems, it behaves differently, right? So what KyJah mentioned is right now, like I think Python also uses the same approach, right? We have Python, which writes stuff to Arrow, and then it takes a pointer to Arrow, gives it to Delta RS, and then Delta RS like writes it using object store or whatever, right?
Yep.
I think like when you're doing I don't know, like data sciencey kind of stuff, like that's fine, right? Like you're not going to be exposing memory allocation errors, but when you're trying to do like high throughput data shoveling from A to B at like massive scale across like 100 pods in Kubernetes, let's say, any literal bug that exists in any library is going to come to you, right? And then you're going to spend hours and hours on kind of troubleshooting it. And just to echo what KyJah was saying, I think the ultimate way to like use this kind of interop runtime is you want to have whatever your native language is write out parquet, right? So reading is different, but like let's say you're just trying to shovel data from A to B. You've got your data, which let's say is coming from Event Hub, right? And it could be terabytes of data that's getting buffered into memory. You want to write to parquet as fast as your internal buffer fills up, and you want to use native languages and like native parquet libraries in order to do that. Because first of all, you're going to have like the garbage collection, which is the most important part of having a language like .NET, right? When a variable goes out of scope, so does your memory. This is a .NET guarantee. When you're using these like Apache arrow pointers and stuff, it is somebody's responsibility to make sure that if something crashes or some exception happens, it's deallocated properly. And when it doesn't happen, then you have problems. And so the FFI is working, and these, like I think some folks at Databricks and some other really cool engineers at DuckDB and whatnot, they're working on decoupling the FFI so that you could update the transaction log using the FFI, which is just a couple lines of JSON, whereas the heavy data movement of Parquet could happen in the native language with metadata transfer.
One thing to keep in mind is, now it's true when your variable goes out of scope, it will eventually be deallocated. Otherwise, there'd be absolutely no reason, right, to use the unmanaged languages. So, it's always about your risk calculus. How much mental overhead are you willing to take in your execution? If you're going to write it in C, well, you're willing to take tons of mental overhead, right? But when you write in .NET, you really get to focus on the problem, potentially at the expense of performance. However, .NET has since what, 7, when the introduction of memory and span, has allowed you to dip your toe in the water of some pretty strong memory management, such that it actually, my preference between .NET and Go for garbage collected languages flipped in that time. It's still not going to approach native performance, but you can keep your memory profile in .NET used to do something like this. Now you can kind of keep memory, in a predictable graph. So it's pretty good now.
What kind of, if you think about this with like the engine, like FFI, and like all like the kind of like the bridge between .NET, where there's like this, at least like Raki, from your point of view, .NET was like your go-to, and then Rust was not necessarily your go-to. What kind of troubleshooting did you have to learn how to do on the fly to make this work, or could you trust just 100% on like just Delta RS?
Yeah. Okay. So I'll show the PR that I put up with regards to these changes, if I can find it. I had to do a lot of like stress testing, right? Because okay, so I'll just share my transparent feedback about the Delta kernel. The current interface that they expose is like very complex, right? I think you have to manage like 15 different pointers to the kernel binding. I'm not able to find it, but 1 second, sorry.
It's okay.
Yeah, let's suppose I go to there's like you'll see from the pointer binding that there's like quite a bit that you as an end user have to do, and like somebody has to manage that complexity, and in this case it happened to be us here. So here, let me show you. So for example, when we added the Delta kernel FFI, which was like this part, there's like, let me get to the actual part that has like all the crazy pointers. Give me a second. Arrow FFI interop handler. Yeah, there's too many files. My GitHub is actually lagging. But yeah, like for example, you can see here, right? Like this is the FFI interface that we have to implement with regards to interoperating with the kernel, and it's a very large interface, right? So like this is all like C# needs to basically give pointers to all of these things, and that was difficult, right? And so like just making sure that I don't have a bug and how we're doing things, that was kind of a bit of a testing situation. But other than that, like once it's stable, right? And you can just throw a large amount of data at it. And then it allowed us to kind of get confidence. Yeah.
That's awesome. So the joyful moments, right? Once everything actually starts to work, or that first day where it actually something happens. That's awesome.
I would like to talk about like what some problems somebody could face when they're trying to basically do this at like outside the boundary of a single machine, right? So let me just kind of quickly walk through some like numbers and some architecture. Just give me 1 second. For some reason, this is lagging. Okay, there we go. All right. So for example, like our throughput so this is a 16 premium 16 PU event hub in Azure Event Hub, and the max that I was able to get out of it is about like 27 gigabytes per minute, right? Which is a high amount of like very large amount of data. You cannot deserialize this from a single Kubernetes pod, which is where we host our app. If you were to like, you would need to essentially have like about 5 times the amount of memory, because you would need to like allocate all this buffer and memory. Right? It's impossible. Or you would need like a very large Kubernetes cluster. So what I had to do, and this is something that KyJah we haven't really chatted about in too deep, but I think I would love to see the kernel kind of implement this. Is that so? Let's suppose you have an event hub and it's partition based on let's say 100 different partitions that you have, right? You're going to essentially need to allocate each of these buffers into a single C# replica, right? That's going to basically, let's say, take like partition 1, 2, and 3, and then it's going to build up like a in-memory buffer of that, right? And then when the size of the buffer reaches a certain number, you want to basically flush it to Parquet. The problem is that given the 27 gigs per minute that I was showing you, I had, let's say, like 10 of these pods that I just spun up in Kubernetes. And when I was trying to use delta-rs in order to do transactions, I would essentially find like the 7 of my pods would essentially just go into like a crash loop because.
Hey Raki, just real quick, are you showing the view from kubectl by any chance?
Oh no, I'm not actually. Sorry.
No worries at all. Just wanted to make sure that we have that showing as well.
Got it. Yeah.
And then also for people in the audience as well, if you think about buffering and you think about like writing to the transaction log, or basically writing the files first and then committing to the transaction log, can you talk a little bit more about that for people that haven't been like living in kernel world, or maybe don't necessarily understand what the difference is between like writing every single record to a file versus buffering and writing a chunk to a file?
So the issue that Raki was running into initially is basically there's no mutex, with these distributed pods. So, and now Delta's atomic, but it's not like atomic because there's a central server doing the coordination. It's atomic because each transaction is accepted. So what you would get is he would have a pod that would write its file and then say, okay, now I'm going to write the corresponding transaction log. Transaction log is sequentially numbered. So if every pod is trying to write transaction number 5, well, one will get to write transaction number 5, and the other 9 will then say, okay, let's try to write 6. And then hopefully one gets to write 6, or the original pod might end up writing 6, and then they just keep doing that, 10, 15, 20 retries, and then eventually, it just explodes and restarts, which is, obviously not an effective thing. And one of the things that, it's the difference between Delta kernel and Delta Spark is that some of these solutions, like Delta Spark is a bigger solution built around the Delta protocol. Delta-rs is also a solution built around the Delta protocol. But one of the things Delta Spark does is when it's working with partition sets, it knows that it can go ahead and write the partition data and then later coordinate the update of the transaction log after the data has been stored, because it's controlling the write path. However, if you ran into a scenario where you were writing from Delta Spark and somewhere else, you would end up breaking everything. So it's kind of the difference between a system built on top of Delta to solve a problem versus, just pure Delta. Pure Delta by itself is useful from writing from a single source. Once it becomes a distributed systems problem, you have to find a way to wrangle your chaos, and that's where Raki's going with this.
I'll share like some costs, right? So I think you guys can see my actual screen now.
Yes.
So this is from a gentleman named at Script from Data and AI Summit in 2022. This number was highly lucrative to me because we spend a lot of money on Spark because we take data from like millions of customers, as I mentioned, right? And any optimization that I'm able to do, it basically saves customer like potentially millions of dollars every year, right? Which is high impact and achieves the same end use case. And so I saw this and I realized, okay, you know what? Like there's something here. This is a ridiculous number of cost reduction, right? So like again, just going back to the quick numbers, right? Like we have a very high amount of data that's coming into the event hub, and there's no way you could like have a single reader, right? So you can't have a single computer unless the computer is like a football stadium, like read from that event, and you're going to run into like network like ISP problems, right? Because a single NIC can't handle that much data. And then you're going to have to like send it all to to Delta using like the in-memory buffer that's in here, right? So it has to be distributed, right? That's something that Spark does, but obviously I don't want the whole beautiful query optimization Spark has. I just need something that can read and partition out of an event hub. And so like when I took the naive approach, so let me go back to the architecture real quick. So you have an event hub. What you can do in an event hub is like it's got partitions, and you can have up to 100 partitions, right? Which means that if you have a stream of data coming in from different sources, it'll just automatically just get distributed across the partitions. The naive approach is you just take a single like C# app that puts these like subscribes to each of these topics, and then each of them go and like try to write to the Delta transaction or the Delta table, right? What the problem is that as KyJah was mentioning, what I was saying is, let's say I had 10 pods, and each of those 10 pods, like let's say took 10 partitions, right? You would never be able to update the transaction log more than like 3 people at a time. That was kind of the empirical observation I saw. Like I was doing a transaction about like every 5 minutes, right? And so if you're doing a transaction every 5 minutes, there's always going to be like a certain number of replicas that are never going to have a chance to do a transaction. And the problem with the arrow, like an arrow backend is like when you send a piece of pointer across the arrow boundary, and then like your transaction fails because like let's say Rust throws, right? That arrow pointer is actually gone. Like it deallocates the moment you've sent it across the FFI boundary. And so when you're like retrying that transaction, you're essentially copying that data from the C# native, let's say like array or map or whatever, and then you're like moving it across the FFI boundary. So it's like a destructive situation because you're always going to have a backlog of data that's coming in that you're never going to be able to get rid of. And that was the kind of like problem that I was really struggling with. And I tried a couple of approaches, talking with KyJah. Like one is using a in-memory semaphore in C#, where you could just have different writer processes, have a mutex that can like go ahead and lock it. That doesn't work because you're essentially just building up an in-memory buffer of data. And the second thing you could do is you could use like a distributed mutex across your pods. So like Azure Blob Store or Postgres or something, where you could have a row that you lock, and then the other guy takes a chance and like locks the row. But still, like at a certain scale, you're not going to be able to flush the buffer. Like the only way you can solve this problem is if you can flush every single partition as fast as the data is filling up, right? It's just basic like data in, data out. And before I talk about how I kind of solved that using like a kind of a workaround that came out of the Delta community from Tyler, I can kind of chat about what that Oxbow project is, if you guys are not familiar with it.
Yes, please. We can walk through that as well.
Okay. So basically, this is from the gentleman who maintains the Delta RS project, Tyler. Very helpful. He's on the Delta community. So basically, the problem he was trying to solve is the same problem I've been trying to solve in C#, which is like you're going to have data that's being sent to, let's say, an S3 bucket, right? And AWS and Azure too, like we have something called Event Grid. They store the metadata for the data files that was added into, let's say, into a event structure. So this Oxbow project, what it does is essentially reads that metadata, and then it goes to the Delta transaction log, and then it does blind defense, right? So basically, you first write to Parquet using whatever process, and then after the fact, it goes and updates the transaction log, which means that when a reader is trying to read the table, they're going to read the data like with maybe like a few seconds of latency, right? This is a very powerful pattern that I think Tyler has started putting together, because what it allows you to do is it allows you to basically decouple the Parquet flushing, which just can happen in parallel, right? Like if you have a folder in Azure Blob Storage, it is not going to stop you from flushing thousands of Parquet files. And then what you can do is you can essentially serialize the transaction log using some sort of semaphore, as KyJah was mentioning. And in this case, I basically used an event hub as that semaphore.
This is for people in like the Spark community who are used to like asynchronous commit logs. It's the same kind of concept as well.
Yeah. And so another way that I've historically addressed this, because well, Oxbow didn't exist, but when I was using Azure a lot, so one of the nice features about event hubs is they have a feature called capture. Depending on whether you're using standard or premium, you can do the cost math. Capture has a price at the standard level; it doesn't at the premium level. So if you're using a premium event hub, I'd say just use Capture if you can. But what Capture does is it actually takes every partition of your event hub, writes it to, Azure Blob Storage in what's the Avro format, and you can set it by size or time interval, and it'll put all those slices there. So now Azure Event Grid is, as Raki mentioned, will then go ahead and just send that list straight to another event hub if you want. Or you can read the log in Azure that tells you what files were written. But either way, then what that actually does is it turns your blob storage into your semaphore, because one reader of blob storage theoretically can keep up with that aggregated throughput. I've used it for Delta, and also because you will blow up Elasticsearch probably trying to do the same thing, but you can index a shockingly high amount of data once you've allowed your tooling to pre-aggregate it.
There's like some KPIs that we wanted to meet for this implement. Like if you think about a system like this, right? Like what are the things you need in order for a system like this to be adopted into production? One is you need to have like at least one guarantee, right? Two is you need to have like scale to zero, right? So for example, like Spark has this implemented. There's like dynamic executor allocation, which means that if a particular executor has been like chilling for 60 seconds, the driver goes and kills it. But you're always going to have a driver node which is alive, right? So like we wanted for my use case, we wanted to have like absolute scale to zero, which means that like for example, we have regional event hub topics, right? Which means that I have an event hub and it's going to have topics. Certain Azure regions probably isn't getting a lot of data. Like let me just say like I don't know, like Antarctica West, right? Like maybe they're not using a lot of data. And so like, I don't want to have a bunch of Kubernetes pods that are just always waiting and pulling event hub, just so when a data comes in Antarctica, we go and like deserializing, right? So you want to have like scale to zero, so you're not paying when you're not using it. And this is where a project called Kubernetes Event-Driven Autoscaler, I'll show it in the demo. It's actually like pretty awesome. It's pretty amazing. So what it does is KEDA, it's got this thing called a Kubernetes operator, which is like nothing more than just like a native custom resource definition Kubernetes, and it basically goes to Event Hub and it does a like metadata lookup saying, hey, Event Hub, in this particular topic in this partition, do you have like some new data for me, right? And then Event Hub is like, well, the last offset is like 50, right? And then what KEDA does is it goes to the Event Hub checkpoint, which is basically in an Azure Blob Storage, where you as a writer, right? So you as a writer process would go ahead and like commit, okay, I'm at like point number 14, right? So KEDA essentially it does a quick reconcile between the last persisted checkpoint, which is 14, versus what's in Event Hub, which is 15. And then what it will do is it will go to Kubernetes and say, hey, Kubernetes, go ahead and spin up this pod. And then this pod will go read that last transaction, commit it into Delta, and then sleep. And so essentially this is like as close as you can get to like serverless data ingestion architecture.
So one of the nice things about KEDA is, if you're not familiar with Kubernetes, there's a concept called a horizontal pod autoscaler, which generally just scales based off of resource and memory. But what a horizontal pod autoscaler does is it takes a measurement and returns a number. And that number is more or less the number of pods that you want running. So outside of the Event Hub autoscaler that exists, there's also a generic gRPC autoscaler that you can implement. So if you have more interesting business logic that you would need to apply, you can actually use that interface for your scaling. So like if you have a time window where you're just not going to scale up, you can add that into there, or I don't know, anything that tickles your fancy, you can pretty much turn into a set of scaling rules for Kubernetes.
And like I know Kubernetes has and us included as well, it's got like a very bad reputation, like, oh, it's complex, you're gonna have to pay people lots of salaries and stuff. Yes, I mean, nothing in the world is free, right? When you use AWS Lambda in order to do your serverless autoscaling, you're paying a premium to Amazon in order to manage the complexity for you, right? At a certain, like when you do a calculation, it is way, way, way cheaper to use Kubernetes at a certain amount of scale compared to like, using a cloud serverless platform. But, you do take on that like tech responsibility within your team. So for example, like when I did a calculation of what we're paying after we move off of Spark in order to do this ingestion, like we were paying something like, let's say $5,000 annually for a job like this. And right now, my team is actually paying probably like $20 in Kubernetes, given that like within Microsoft, we can also do something, or within Azure, you can do something called like discounted node. So you say, hey, I'm going to use this Kubernetes node for like the next 5 years. So I've like committed to it. And so like the cost benefit, it just like ridiculously goes down when you're using Kubernetes.
You're talking about reserve pricing?
Reserve pricing, exactly. Yeah. So it's like a very, so basically when you couple like a good library like delta-dotnet that allows you to scale without, like memory issues and stuff, when you combine an architecture that is horizontally scalable, and when you basically have reserve pricing, like it makes this architecture very modern and future facing. I can show a demo of like a quick like what happens when an event comes in. How does Kubernetes scale up the pod? Scott, if you want, I can.
Yes. Yeah, I think that'd be awesome. I think because
do it.
KyJah, you go.
No, I was saying go for it. Do it.
Awesome.
Let me know if you guys cannot hear the audio. Okay.
I think the audio is not coming through.
Okay, let me try one more time. Give me 1 second. Share screen. Let's try video file actually. All right.
I know this worked because we did the trial of this before. It might be that like a sound level just will be turned up like
okay, got
on
it.
your laptop as well.
Understood. Share screen. Entire. There we go. Okay, let's look at a quick demonstration of this delta-dotnet sync in action. So essentially, I'm going to have a Kubernetes cluster, which is going to have KEDA operator pre-installed on AKS. Can you guys hear that, or?
Yes.
Yeah.
Coming through loud and clear.
Okay. And I'm going to have an event hub, 3 topics, essentially. So 3 of these. And what we're going to look at is we're going to be running 0 replicas of the delta-dotnet worker. We're going to fire some events into the event hub. And we're going to look at how KEDA spins up these workers into high replicas, and how we do a bulk load into a Delta Lake sync. So let's take a look at that in action. So just to kind of orient with regards to my screen, on the top left here, these are 3 event hub topics that I have. On the bottom left here, I have an empty OneLake Azure storage account shortcut. On the right here, I have K9s, which is a CLI tool in Kubernetes. And you can see I've got the KEDA operator, and my 3 workers are currently dormant, and so is my bulk loader. So essentially in KEDA, this is called a custom resource definition, which is how we tell it to scale. And so we've told KEDA that the minimum number of workers is 0 and the maximum number of workers is 2. And currently, if I go into my Kubernetes namespace, you can see there's no pods there because we don't have any backlog of events, right? And the Delta tables, as you can see, it doesn't exist. So what I'm going to do is I've got 3 tabs open with each of these topics, and I'm going to go in, and I'm going to go ahead and send some events per topic, right? So let's go ahead and do that with this yellow taxi data. This is a cool tool that the Event Hub team made to send some data. So let's say we're going to send about 1,000 events. I'll go ahead and do that. Click on send. And essentially what's happening, so those 1,000 events got sent. So just to go to the diagram while this spins up, KEDA is essentially observing that topic that we send data to. and it looks at the checkpoint, which currently doesn't exist, and it basically goes ahead and says, okay, well, there's some new data in this topic that needs to be processed, and that hasn't been checkpointed, which means there's data that we haven't processed. And you can see that it basically spun up a single replica of my .NET Sync, which is essentially this guy, right? So it spun it up, and I do a refresh, and you can see that the work is already done. So that .NET Sync process, it basically sensed that there was a piece of work that needs to be done. It went ahead and created that the parquet flush, so you can see it's partitioned based on that, and it sent a event to the delta bulk uploader, which went ahead and did it for it committed that JSON. So now what we're going to do is we're going to do this across multiple topics. And you can see it's scaled back to 0, which means we're not paying for computers and stuff. So let me go ahead and do that across 3 regional topics. In this case, that's kind of what we're simulating. So let me just align my screen. This is going to be for 1,000, and it could be any number. I'm just sending 1,000 just to see it working. It could even be like 1 event. You can tell KEDA how many events you want it to watch for. So let me go ahead and do that with 1,000 and 1 more. And we're going to repeat fire those 3 together to see all 3 workers spin up in action. So 1, 2, and 3. So what we're going to see in the bottom right of my screen is 3 different worker pods are going to come up for each of those topics. So you can see all 3 came up because the KEDA operator, which is this guy right here, it went ahead and basically sensed that diff between the topic and what's checkpointed. Done. You can see each of those workers wrote the delta transaction, and then my bulk loader, it sensed in its event hub that there is work that needs to be done. It did that work, and now if I do a refresh, you will see all 3 delta tables. So these are new. North Central, you can see there's 1 delta transaction entry. Brazil South, there is 1 transaction entry, and the one that we had previously, when we did the original, which is Australia, it should have 2 parquet files, each containing those 1,000 events, and it's got your 2 delta transaction logs. That's it, and the replicas are now at 0. Thank you.
Awesome.
One of the things that I kind of want to share that I learned a little bit of Rust, mostly from seeing KyJah's code and how things are done in Delta-RS and stuff. C# has a bunch of primitives. You could await a task with a task completion source and send that receipt back to some other guy and then await that, right? I don't know how to do that in Rust. KyJah, I'm not sure if you've, based on your experience with both languages, what would you say with regards to doing hard things in both? And
so Rust has async await, right? Which but Rust implements a future which has a poll method, and the same thing can be done. We return pending or ready. However, it'd be great if C# and Rust could speak directly. Like Python and Rust can speak directly, but really Pyo3, which allows you to make it seem like you're interacting with Python and Rust, really just hides all the C magic in the background. I think I saw a .NET project where someone began to do that, but it's substantially more work than just dealing with the CFFI. So the way you end up doing async and await across the boundary with the .NET Rust, or I'm sorry, .NET C and Rust dance, is you will use a task completion source on the .NET side, and then you pass a callback through across the FFI boundary, and then Rust will just execute that callback method in the end. And then once the callback method is executed, you complete your task. So and was it try exception, try set result, or there's one other try method on there. Right. Now the hardest thing about dealing with the FFI and .NET work is that there are quirks. .NET has garbage collection. It's not perfect. There are still bugs. That's why new versions are released. That's why it gets patched. Yeah. So if you call set result on a task completion source, It's probably going to work, but it might not. And your and your process might just deadlock. However, if you call, or no, it's not, if you call try result or try set result, it'll most likely work. But there are times it won't work. So you hide it in a task and call it. It calls it asynchronously, and it just works because ultimately every language there's a bunch of C code somewhere magically in the background doing the worst part about it, or there's unsafe code somewhere in it. And once you write one line of unsafe code, you've assumed a level of risk that didn't exist before. Like Rust, while it doesn't have garbage collection, I think someone mentioned shared pointers in C++.
Right.
Effectively, in Rust, as long as you've written completely safe code, your program knows at compile time the life cycle of every object within the program. So that's how you don't have to manually drop and delete things, and you get the effective behavior of garbage collection as long as you make the borrow checker.
With the annotations and lifetime specifiers and stuff.
Right.
One of the things that when I look at a project like this, right, like delta-dotnet, the fact that we're building it, I think it serves a higher vision. And let me explain what I mean by that. If you look in if you go on Google and you search for delta C# NuGet package, we're not the only one. There's 3 or 4 other brave souls that have looked at the delta Scala code, and it's I'm going to reinvent the wheel this morning. And then they basically just took the delta transaction protocol and wrote pure old C# code that will do the add files, remove files, and all that good stuff, right? I actually went down that route because I was I'm gonna do it. It can't be that hard. It is that hard. There's V1 to V7 or V8 today with Delta, and especially when you're doing writes of data, there's so much because if you think about it, right, Delta Lake is essentially a database engine. It's a database engine that sits on commodity Hadoop hardware or your hard drive, right? It's taken what databases like SQL Server and Postgres have done, yanked out the transaction governor, and then put it into commodity hardware. Now, if you do that without a computer running all the time that's doing the governance of transactions and conflict checking, you're going to need a lot of complicated client-side code in order to do that, right? And all these, I guess this is why Spark is so successful in the industry, because I think it's got the most complete set of Delta read and write transaction support, the smart things that you can do with Delta, right? Merge on read and deletion vectors. These are very non-trivial database concepts that are in the Spark code base, because Databricks and these other folks have a bunch of PhDs that know databases really well, right? If you're not somebody who's lived in that mindset and that industry, you try to do it in C#, you're gonna commit a bunch of bugs. And the last thing you want is to have a table where your end users don't trust the data because you've got bugs in it, right? So in my opinion, using a language to build a transaction protocol from scratch and covering the whole surface area, it's a fool's errand unless you're employed by somebody who's in that business, right? So for example, I know the gentleman who built the Delta RS, I think the original committer, he kind of he was one of the only people that I think did a really good job. And if you look at the Delta RS repo, he's got TLA plus proofs, which is a way of doing distributed systems guarantee checks and stuff. And it's all mathematical guarantees. And there's not a lot of people that it's not code that. At that point, you're doing distributed system consistency checking, right? So the point I'm trying to get at is anybody who tries to build these Delta read write, or not even Delta write, Hoodie or whatever in native language, you're essentially going down a rabbit hole where you're not going to be able to maintain that project unless it's part of a larger vision. This is where I feel the Delta kernel takes that complexity and abstracts it away into the engine as it should be, right? Take all the juiciness of Spark, put it into a little FFI layer that anybody can invoke. You just tell it what metadata you need to write. You just tell it what parquet you wrote or whatever, and then you let the complexity hide inside the kernel. It's a very promising project that I think solves one of the hardest problems in the database industry, which is doing databasey things without actually running a computer by using a client-side SDK. And that's why, I'm really glad that with KyJah, especially, I'll be honest, what he put together with wrapping the Delta RS, it showed me things you could do in C# that I don't think is well documented. For example, the CLang invoke generator, where you take a FFI header and then you generate C# classes automatically. That stuff's not you can't just go Googling for it, right? You have to learn it and know it.
Yeah.
And yeah, long story short, we have a really good pattern in the repo to be future facing.
Well, yeah, I mean, well, FFI in general, the P invoke is generally, unless you're invoking like a native library that's probably already on the system, generally outside the scope of what you're going to do in, almost every .NET project. It's always been a rare case for me. Like, I think, back in the day, maybe I had to do it for an imaging library, because GDI wasn't enough. But I didn't, in the 7 or 8 years after that, didn't have to do it until very recently. So, but yeah, there's a lot that you can accomplish in C#, but there's a lot that you don't want to implement. We talked about the emotional cost of, hey Denny, of implementing something yourself. Like, what is it buying you? If that extra work isn't proprietary, or it isn't saving you something, or is it really adding value to your life, you probably shouldn't do it. Now, the existing projects may not meet your needs, but that's why you jump in the repository and say, hey, I'd like to make some changes. Can we make some changes? And if the answer is yes, then you should probably jump on that. If the answer is no, those are probably bad people that you're working with. Like, the idea here is to build something that helps a lot of people solve a lot of different use cases. And that may mean that this repository is right now may need to evolve into multiple libraries so people can pick and choose what they need to use. Like one of the primary tenets of Rust is only, using what you need. You only pay for the stuff that you want. Right? We don't need to build a Cadillac library, but we should open the door to making that possible while keeping things simple and leaving the minutia to the kernel. There are people that are spending plenty of time working on making very Delta specific functionality usable by everyone. And then you can do the thing that .NET's good at, implementing your business logic and helping you make some money. That's where we want to be ultimately in our implementation.
Not to mention, like, the Event Hub NuGet package that exists for .NET. It is a piece of art. So I spoke to the if you use like RD Kafka or something, right? Like, you got to do like partition rebalancing. Like when a pod dies or something, and then there's like a rebalance signal, like, you have to handle all that yourself, right? You have to keep your own in-memory buffer where you're polling Kafka and building it up. Event Hub does all of that. They've got this like super fancy algorithm in the C# NuGet where they're like eagerly polling using like a task factory. So the point I'm trying to make is C# has a lot of like business problems that have been solved using like abstractions that companies, is like, especially Microsoft, as you guys probably know, like, we're one of the key like sponsors of C#. It's a very great language that helps you solve business problems without getting into the system nitty gritty, right? The Delta kernel, on the other hand, is nitty gritty. It's a very, very nitty gritty project. The CFFI layer is extremely complex. You're dealing with pointers. Like, this is not something you could just go to ChatGPT and be like, hey, give me a piece of code that's like like unsafe and it's going to compile. Like, no, like, you have to test it, right? You have to go through the nuances, and I think it's a good combination.
Yeah, one thing I'd love to add to a little flavor to all this, and thanks very much for inviting me, guys, to join you, is that when we first created the Delta Rust, right, like the whole API, it was QP and it was, Tyler and all these other folks. It was really interesting because we actually asked ourselves the exact same question, right? And like, it was like, should we just piggyback off the Scala APIs? Why bother building Rust? And then and the funny story is, like, I was if you ever, by the way, are really into Rust, the guy I would follow is a guy named Frank McSherry, and this guy is brilliant. I think he's still the CTO of Materialize, co-founder and CTO of Materialize, for a streaming database. But the reason I bring it up is because I'm definitely aging myself now. Okay, so back in 2017, he and I were having, not 2017, sorry, 2007. Excuse me. He and I were having these debates about, like, and this is when he and I were both working at Microsoft, and about, like, should we distribute the problem, or should we go ahead and go ahead and actually be more efficient with the CPU, right? And then, of course, that turned out to be more efficient CPUs Rust, and then me distribute everything. Of course, I'm in Spark, right? So, of course, now I'm Mr. Spark boy, la, 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 la. And then about 4 or 5 years ago, I'm going, because I'm thinking up to this point, like, no, I won the debate with Frank, right? And then about 4 or 5 years ago, after I see how much more efficient everything is, I'm like, oh, crap, I think Frank won the debate. Like, yeah, so it's that shift. And so to your point exactly, right, we realized there's a lot of efficiencies that we could do with Rust, right, which is great. So that's why ultimately the Rust API was created. But then to your point exactly, as we're progressing, we realized we made all of these mistakes. And so that's literally what kernel is. Kernel is like, okay, we made a ton of mistakes this last 4 or 5 years. Let's go ahead and not do those mistakes. Let's fix all the mistakes we made, create kernel, so that way, to your point exactly, .NET integration, later on Golang or any of the other languages, it just becomes a lot simpler because we're going, let's just build kernel, y'all can hit that, and then you're good to go. And then all that cool business logic that's in delta-dotnet, perfect. Let it fly high, and meanwhile, we'll take care of everything else from the kernel perspective. So exactly, I love that you guys called it out, and I love that you guys like came to the same conclusion. I just wish we had came to that same conclusion a lot earlier than we did. That's all. So
I think one of the other interesting things too is if you think about like the kernel as like a kind of a traditional interface that's like super powerful. I think of this kind of like gRPC, right, where it's like I want to go and I want to implement an idiomatic like SDK for a new language, whether it's Go now for the kernel or anything else. It's nice to have the primitives and then also be able to create an API that's usable by people within, say, the .NET community and the Golang community, because the ways of working are different. And I think it's nice when you see like the kind of that level of effort being put into a library so that it feels natural for people who are coming from, being in, I was in C# land for like 5 years when I was working at Yahoo. And I was working on like games. We were using like XNA for Xbox 360, and that was when I think this was back at like C# 4.5 to 5 era back in the day. But it was completely different if I was using C# than if I was using Java, than if I was using Python, than if I was using Scala, etc. And I think that's nice to be able to just have like an idiomatic interface as well. Is that something that you see kind of evolving onto the kernel as well? Kind of more of those ties.
The personal, like, go ahead, KyJah.
I was going to say, I mean, that's at least, there are weekly meetings about the kernel, and generally the discussion is, what is the purpose of the kernel? I mean, that's still a little bit in flux, but, to some extent, the kernel is there to provide your guide rails. To tell you the what's and hows, or not necessarily the hows, but what you should be doing, when you should be doing it. But you can do the implementation details, and there's the option of pulling in the default engine, and maybe that will do more. But in the grand scheme of things, maybe a perfect kernel would provide callbacks to say, well, because this delta setting is here, like auto compaction, you should probably be running vacuum here or optimize. But not necessarily actually invoking, the functionality for you, which suddenly allows you to build substantially more interesting products on top of Delta without, necessarily needing to make extensive changes to the underlying library. So you want to open the door.
There's a very successful telemetry standard that has taken over the industry. It's called Open Telemetry. You guys might be familiar with it, OTLP. So like what these guys did was they just took like a crazy, like Denny was saying, like we took mistakes that existed in the open source telemetry system, and then they like got all these like smart folks together, like, all right, let's build a protocol that we can use to like send data of any kind with a common language, and that can be invoked via any programming language, right? And I think that same mentality is being applied to Delta kernel when I look at the project, right? Like these OTLP people, they have like these primitives like plog, ptrace, pmetrics, and it's like very low level implementations in Go with regards to like highly performant like message buff, and like just things that you're not going to be working with on a day-to-day basis. And I feel like maybe in the next 3 years, 4 years, I would love to see the Delta kernel, like not only would it generate the FFI header, which is how you speak to the kernel and the public interfaces, but there's nothing stopping them from following what OpenTelemetry did, and also like generating language-specific bindings, right? Like there's no reason why the kernel shouldn't have a lot of that logic, and build bindings for C#, build bindings for Golang and Java or whatever else, right? I feel like if ever Spark is going to itself use the kernel at one point, because I don't think there's going to be a Spark rewrite in Rust anytime soon. Like that's going to be a behemoth of a project. Spark is either going to keep all that Scala code of doing conflict checking and stuff, and like outside of the kernel, and like let's be honest, I think if it does that, it's going to become obsolete, right? Because you're going to have to keep logic in two places. If the kernel is going to rise, Spark has to delegate the problem statement of writing and reading delta to the kernel. And when that does happen, I think we would have to make sure that there's like a lock. Like you can't have an FFI implementation in Spark that's not in sync with the commits that's going into kernel, right? Then it's just going to be a mess. So I think at some point, Nick and those folks, they're going to have to like look into solving that problem. Yeah.
Well, just as a little drop on that, you can always join us every Thursday in the Delta Kernel RS meetings where we actually discuss some of these things. And then I have to freely admit, there's parts of us going like, can we just solve the whole thing in Rust and then have Spark go talk to it? Now, I know that's blasphemy, especially for somebody who actually wrote, the Learning Spark book, the most recent Learning Spark book. So, but yeah, like there's actually thinking around that. Obviously, this is definitely much up for debate. So nothing's been decided. But like I said, every Thursday, 10:30 Pacific, there is the Delta Kernel RS meeting. So if you want to join, just let us know.
I think it's also, adding to that, Denny, it's interesting because if you think about like the PySpark library, right? Like it is functionally just going through like a Py4j to make calls to the Java layer. And it's interesting because if you think about like before we were talking about Py03, which is making calls directly to the Rust layer, a lot of there's that kind of synergy between like those conceptual ideas. Which I think would be interesting in general, like to see Spark move even faster, because I think for people in the Spark community, I've been in the Spark community since like 2016. It's interesting because it's like every big major release, not relief. Anyways, like it's been a relief that, but every major release is giving us tons and tons more performance. I think it's interesting, like if you were to go from like 50% better performance, 100% better performance, 10x better performance, up to like 1000x, because you've then gone to Rust. I think people would be completely fine with that, right? It's it is a powerful set of tools for any type of engineering problems. But then again, it's there's a lot of like that there's a lot of people's time and effort that go into it. So it's always hard to walk away from those things as well and be like, oh, let's just replace it with something, something better. But I could see
there's
that.
A question in the chat about, it's addressed to Raki about running delta-dotnet in an Azure function. However, I think I can answer this question. Simple answers: don't do it on ARM. There's a bug. However, there's an issue actually if you go to the delta-dotnet repository specifically addressing that it wasn't working in an Azure function, and now we've gotten it to at least a working state if you're using x86, and there are people running it on Azure functions that you actually may be able to ask them directly what their experience is, because Raki's using Kubernetes, and I pretty much only run things on Kubernetes, so I have a lot of experience with that.
There's a format of Azure Function where you could give it like a Docker image, just a plain old Docker image, and then it'll auto-scale for you. I think to the gentleman who's asking the question, that might be like a better way because all your dependencies at the OS level is captured. There's another form of Azure Function where you like use this this wrapper thing where you have to invoke, like you give it a post API call or something, and then it just like wraps it in their HTTP library. In that case, I think you might run into more of the issues that KyJah was saying, because you're not controlling the runtime and dependencies, right? So we might have some issues with Rust or the SSL library. So I would say go the container route. Yeah, it's going to be just like Kubernetes.
So there's a question about Spark being redesigned or rebuilt using Rust, and that's probably never happened. However, there are alternatives to that. So, for example, there's a library called Apache Data Fusion Comet, That data fusion is written in Rust. And what it is basically an engine plugin for Spark. So you can actually use that as your runtime for your Spark environment. So actually, in that example, you could probably even use Delta RS or Delta kernel or something built like that if you wanted to write the necessary bridge code. And if you're worried about the stability or usability of it, I believe Apple and Amazon are both using it in production, and they've experienced some pretty dramatic cost savings with that. And I think at Databricks, you guys are still working on the Photon engine, right?
Yeah, so both actually. So we're working on the Photon engine, which is our own native engine, right? But yeah, we're supporters of Comet as well. So Andy Grove, that's the guy who actually has created. He actually left NVIDIA to join Apple specifically to do this. Exactly to your point, KyJah. Like it's a pretty cool project. So a lot of the learnings, like from Ballista, which would be if I was to say, for example, Spark is the Scala Ballistas to Rust, right? If I was to use that particular analogy.
Yeah.
That a lot of those learnings of Ballista, which is part of data fusion itself, that's actually being employed within Comet. So it's actually just like you called it, KyJah, it's Apache Data Fusion Comet, but it's also known as the Apache Data Fusion Comet Spark Accelerator. All right. So we toss in lots of words, but basically the Spark community and the Comet community are actually working together as well. To everybody's point when they're asking questions like this, there's a lot of really interesting things within the Rust community, and a bunch of us, including nerds like myself, we're going like, let's go ahead and start playing with it, see how we can push it. So
the one thing that Spark, I feel like I'm a big fan of Spark, and I love what you guys like, Matei and actually Reynold was. We went to the same university, so like he was like Smarty Cookie back in the day. Like Spark has solved such a hard problem in the data industry, which is like repartitioning and reshuffling, all doing it in memory in a scalable fashion, right? Like if you look at these like Rust projects, there's one called Arroyo. I think it supposedly does like streaming. Like it's a shame that Rust wasn't big when Spark was being written in 2013, because if it was written in that language, like it would be completely unstoppable, right? Like even today's the Spark code is very modern, very high throughput. The only gap that it has is the fact that it runs on a JVM, right? Which like it's not Spark's fault that it runs on a JVM, it's the underlying language's fault, right? And
but that's actually one of the benefits of these engines, like Comet and Photon, is that Spark, as the driver is relatively lightweight. The executor is always where things could potentially get out of control. So that basically allows you to use the driver as an orchestrator for your high performance compute cluster at that point. So that actually saves you from having to rewrite Spark, because that was never really going to be your bottleneck. At that point, you'd just be rewriting it for the sake of purity, which I mean has never stopped anybody, but not a necessary undertaking.
Awesome. I think we're just about at time. So is there any Raki, KyJah, Denny, anybody have final words, final thoughts, places we want to leave the audience for today?
I'm really glad to be part.
Go ahead, Raki.
No, really glad to be part of this community. Recent joiner. Really glad to meet KyJah. Danny, I think we worked together previously. Scott, thank you for having me. I look forward to kind of contributing some of the new issues that we want to have and the improvements in delta-dotnet, KyJah. And thanks for being so great to work with.
Yeah. So what I was going to say is really we're just looking for more input, more eyes, more use cases. As a person who spends the majority of his time writing code in Rust, I have a very different perspective of using .NET than I had, 2 or 3 years ago. So it's important to have more voices in this conversation. Even if you're not going to provide implementation, you can help provide use cases and understanding and perspective to really help us get a good roadmap and shape the future of this library.
Awesome. Yeah, Denny, you go.
Oh, I was just simply saying I really appreciate both of you actually for joining, for pushing ahead delta-dotnet, and of course KyJah with the delta-dotnet and delta Rust. So yeah, Raki, definitely excited to work with you even more. Ironically, now that we're in different companies, we get to work more together. So just gotta love it sometimes, but it is what it is.
I might do a Golang port as well. The Rivian one, I'm not sure.
Yeah. Actually, that's literally my next meeting right now. So.
Okay. That'll be huge, yeah. If we can bring it into the Delta incubator, probably, and
Oh heck yeah. No, we'll actually have a little bit more to talk about it actually at this Thursday's meeting. In fact, no joke. Yeah. So yeah.
Cool, man.
Awesome. I think with that, I think we're going to close out for the day. And thank you everybody for popping by on this Tuesday morning. All right, cheers.
Thank you.
Nice.
Bye.
Take care, everybody.
Good afternoon. Bye.